Good day, everyone. Today, I'll be introducing the topic of heavy metals in food. Heavy metals are naturally occurring elements like lead, mercury, cadmium, and arsenic. While small amounts exist in the environment, they become dangerous when they accumulate in our food supply. For example, in crops. These metals don't break down easily. Once they enter soil, water, or air, they can be absorbed by crops and animals. Over the time, they build up in the food chain, meaning what looks fresh and healthy on the supermarket shelf may carry hidden risks. For example, rice often contains arsenic, leafy vegetables can absorb cadmium from polluted soil, seafood like tuna and swordfish may carry mercury, and even fruits can show traces of lead when grown in contaminated areas. The danger is that these metals can harm consumers even in small amounts. It affects children's brain development. Mercury damages the nervous system, cadmium weakens kidneys and bones, and arsenic increases cancer risk. These impacts make heavy metals a serious food safety issue worldwide. So, heavy metals are invisible but powerful contaminants, and understanding their risk is the first step toward protecting public health.
Good morning, my name is Adibanisa and I'm going to explain the second part. An optical biosensor is analytical devices that use light to measure the heavy metal toxic in food. There are three main components such as biorecognition elements such as antibody, aptamers, and even DNA probe will bind to the target heavy metal ions such as cadmium, mercury, and even arsenic. This interaction then converted into the second component, which is optical transducer, which they will produce a changes in properties such as fluorescent intensity. Finally, the signal processor analyze the signal and display the concentration of heavy metal on the device. According to the recent studies in 2022 by Wang et al., the fluorescent optosensor has been successfully developed for mercury detection, which demonstrate high sensitivity and also rapid response time. And also, in addition, in 2023, studies by the Chi et al., a fluorescent chemosensor has been applied to detect mercury in river prawn sample, highlighting its potential application in seafood safety monitoring.
One key technical challenge in biosensor is achieving high sensitivity and selectivity. The sensor must detect very low concentrations of a target substance while also distinguishing it from similar compounds in complex samples. Detection limits and accuracy are critical. Poor performance may lead to false positive or false negative, affecting results. Sensor stability and sample preparation also strongly influence the reliability. Developing biosensor technology requires significant investment in research, equipment, and skilled personnel. Costs also increase during large-scale production and real-world implementation. Commercial success depends on both performance and affordability. Even advanced biosensor may face limited adoption if costs are too high or if cheaper alternatives exist. Biosensors must undergo strict validation to ensure accuracy and reliability. Regulatory bodies require thorough testing under different conditions before approval. Regulatory acceptance and standardization remains challenges. Different regions follow different standards, making global adoption more difficult and slower. Public confidence is essential. Users must trust the results, and industries must ensure transparency, quality control, and also ethical responsibility. Inaccurate detection can lead to serious consequences, including risk to health and safety. Maintaining public trust requires continuous improvement and reliable performance. Overall, addressing these technical, economic, regulatory, and ethical issues is the key to successful biosensor adoption.
To successfully bring optical biosensors into the real world, we must look at 5 different groups of people. Each group has their own unique goals and challenges. We start with consumers who simply want safe food that is completely free from heavy metals. However, because they do not know much about this technology, they will only accept it if it keeps their groceries cheap and safe. Linked closely to them are food manufacturers who care most about speed. They need sensors that check food rapidly so factory lines do not stall. Their biggest hurdle is that thick food ingredients can block light signals, making testing difficult and expensive. This directly connects to food safety regulators. They are the officials who write the food safety laws and acts. Their main challenge is that they cannot change these strict laws for a new technology until it proves it is just as accurate as traditional laboratory testing. Moving down the supply chain, we have farmers. They need cheap, portable tools to test their soil and water early. Their technical problem is that muddy water and dirt scatter the sensor light, which makes the field results inaccurate. Finally, we have academic researchers who build these sensors. They want extreme sensitivity and use advanced materials to find tiny amounts of metals. Yet, their main struggle is that these lab designs are often too delicate or complex for a real farm or factory. Therefore, balancing all 5 of these different viewpoints is the true key to success. We can bridge these gaps by using advanced materials like artificial enzymes and smart computer software. These new technologies can clean up noisy data and improve sensor accuracy, making it possible to satisfy the farm, the factory, and the regulators all at once.
Despite their rapid and sensitive detection capabilities, optical biosensors still face challenges such as limited stability, environmental interference, signal disruption from complex food samples, and high development costs. Future research will improve optical biosensors using nanotechnology, AI, and advanced materials to increase the sensitivity and reliability. AI will also help to analyze signals, and future sensors may detect to multiple heavy metals at once for faster food safety testing. Using nanotechnological improvement like stronger bioreconnection elements, better optical transducer, and lower cost production can enhance the biosensor. Smartphone integration and cloud-based system will improve the portability and enable real-time food contamination monitoring. Optical biosensors will not replace the conventional methods such as AAS, ICP-MS, which remain the standard for accurate analysis. However, they can complement them by providing fast, low-cost on-site screening before lab confirmation. For Malaysia, biosensor implementation requires collaboration between government, university, and industry, plus stronger R&D funding. National standard, local production, and food safety integration will improve the reliability and public health. For Malaysia, biosensor